Assalamualaikum and hi to Dr. Ibrahim and fellow friends. We are from Group 4. Today we are going to present about the chemistry and application of thorium and uranium. Before we proceed with our presentation, I would like to introduce the group members. First, Priyameeta Vennu, anak perempuan Vennu. Next, it's me, Siti nooraziehaa binti mohamad zahar. We have Fatin Syamimi binti ahmad shukor and Fatin syakila binti ahmad shukor. So let's start our presentation with a chemistry of thorium. Thorium was discovered by the Swedish chemist John Jacob Berzelius, and thorium with a symbol Th is placed in F block element. It has electron configuration radon 6d2 7s2 and known as actinide family. It has more than 2 dozen of isotopes. For example, thorium-232 isotope with a longest half-life, about 14 billion years. Next, thorium is extract from the mineral ores such as monazite, thorites, and other elements and other minerals. So here I show the flow of extractions thorium. First, from monazite, it will converted into the thorium dioxide. Then the thorium dioxide later will heated by the calcium and produce the free element. Thorium also have 4 oxidation state, which is oxidation state 1, 2, 3, and 4. The chemical properties of thorium, it's soluble in acid and reacts slowly with oxygen due to the low radioactivity. Thorium most stable at oxidation state 4 or thorium 4 when in aqueous solution. Hence, it dominates the solid state chemistry of the element. Commonly, the thorium 4 have a 8 coordination number. For example, we have theta-chloridothorium in dodecahedra geometry and tetrafluoridothorium in square antiprism. The coordinations number 11 usually is exhibited by thorium tetranitrate pentahydride. Next, the physical properties of thorium. It's similar to the lead, which is have silvery and soft metal. Due to properties of metal, it can be hammered, rolled, bent, cut shape, and welded easily. Thorium also have higher melting point and boiling point, which is the melting point is 1800 Celsius and the boiling point is 4500 Celsius. The density of thorium is 11.7 gram centimeter cubic. Here the example of geometry in thorium 4. First, pentagonal bipyramid, octahedron, cubic, bicep square antipyramidal, square pyramidal, and dodecahedron. Okay, I think that's all for me. I will pass to the next presenter.
Okay, so now we are going to see the chemistry of uranium. Uranium is a radioactive chemical element that has a symbol of U and is located in the F block element. It has an electronic configuration of radon 5F3, 6D1, 7S2 and an atomic number of 92. Uranium is from the actinide family and has a relative atomic mass of 238.029. Uranium exists in 3 natural isotopes, namely uranium-234, uranium-235 and uranium-238. Okay, now the physical properties of uranium. It has a density of 19.1 gram per cm cubic. It has a boiling point of 4131 degrees Celsius and a melting point of 1135 degrees Celsius. It is ductile, which means that it can be made into thin wire, and malleable, which means that it can be made into thin sheets. It has silvery white appearance as can be seen from the image here, and it's a dense hard metallic element. Uranium exists from oxidation state of plus 3 to plus 6, but only plus 4 and plus 6 is stable enough to have any sort of practical importance. So example of uranium in the plus 4 oxidation state is uranium dioxide and uranium tetrachloride, and uranium plus 6 is uranium hexafluoride and uranyl ion. Uranium plus 3 is not stable because if you dissolve it in water that has no oxygen, it will still oxidize. That shows how unstable it is. And uranium in the positive 5 oxidation state will usually disproportionate to form uranium plus 4 and uranium plus 6. Uranium metal does not form a passivating oxide coating. So passivating basically means to make the metal less susceptible to corrosion, usually you will coat it with some sort of material such as oxide. The problem with uranium metal is that it does not form this passivating oxide coating. So if you expose it too long to air, it will become corroded. Uranium can be extracted by using conventional uranium mine and mill. So uranium ore will be extracted from the earth by using underground shaft. It will then be transported to a mill where it will be crushed and it will undergo chemical reaction to separate the uranium. The uranium will then be concentrated to form yellow cake. So as can be seen from the image here, it is yellow in color, which suggests the name yellow cake, and this is basically uranium oxide. The another way you can extract uranium is by extracting neutral uranium nitroso complex. So this complex will be extracted from the aqueous phase to an organic phase. So example of organic phase is tributyl phosphate that is dissolved in hydrocarbon solvent. So this technique is not only used to separate uranium, you can use this technique to separate actinoid from fission products in spent nuclear fuels. So spent nuclear fuels is basically nuclear fuels that has been used. The half-life of uranium is uranium-238 is 4.5 billion years, which is approximately the age of our Earth, while uranium-235 has a half-life of 700 million years. Uranium-238 is the most abundant as it has a relative abundance of 99.275%. So although it takes a really, really long time for uranium-238 to decay, as can be seen from the half-life, it is barely radioactive. However, the zero point 0.1 watts of decay heat released by the uranium-238 is actually enough to heat up the Earth's core. Next, I'm going to pass to Kila to explain more on the chemistry of uranium.
Okay, now I will explain about highlights of uranium. Uranium highlights are known for the full range of oxidation state, which is it consists of uranium 3 ion to uranium 6 ion, with a trend toward the decreasing in the coordination number with the increasing of the oxidation number. The most important fluoride is uranium hexafluoride, which is synthesized on a large scale from uranium dioxide. If you guys can see from this reaction, uranium dioxide will react with 4 hydrogen fluoride in order to produce uranium tetrafluoride and 2 molecule of water, and 3 uranium tetrafluoride will react with 2 chlorine trifluoride to produce 3 molecule of uranium hexafluoride and chlorine atom. Okay, the high volatility of uranium hexafluoride, which is sublime at 57 degrees C, together with the occurrence of the fluorine in a single isotopic form, will account for the use of this compound in the separation of the uranium isotope by gaseous diffusion or centrifugation. The uranium tetrachloride is a useful starting material for synthesizing many uranium 6 ion compound and is made up by reacting the uranium trioxide with hexachloropropene. Okay, the uranium atom is non-coordinate in solid uranium trichloride, and which is this is the geometry, and 8 coordinate in uranium tetrachloride. Okay, this is it, geometry, and 6 coordinate for uranium 5 ion and uranium 6 ion. Okay, for uranium 5 chloride and uranium hexachloride, both of them are of which are molecular compound. Okay, and now I will explain about the application of thorium. Thorium is radioactive, so its uses mainly lie in nuclear fuel application. And next, it is also helpful in radiometric dating. Radiometric dating is a method of dating geological specimen by determining the relative proportion of the particular radioactive isotope that present in a sample. Okay, that it is also used as an alloying element in magnesium in order to coat tungsten wire in electrical equipment. Okay, it is also used in nuclear reactors because as it does not generate the plutonium, so it is suitable for nuclear reactors. And the last one, it is used in manufacturing of lenses for cameras and scientific instruments. It can incorporate as much as 40% of thorium dioxide in the glass mixer that can increase the index of the refraction of the glass while at the same time can maintain the low dispersion of the glass. Okay, thoriated glass element can allow the lenses to deliver low levels of aberrations and distortion with relatively simple and easy to manufacture design. Okay, that's all for me. I will pass to the next presenter.
Okay, guys. Now I will explain about the applications of uranium. Okay, as we already know that the radioisotope uranium 235 releases so much energy, so it can be used for efficient power generation in nuclear power station or in devastatingly powerful nuclear weapons. Okay. However, uranium has several other uses because it is 18.7 times as dense as water, so it is often used as ballast in airplanes and boats. Okay. Besides that, uranium 235 is very rare, but uranium 238 is much more common and can be converted to plutonium for power generation. Okay. Next, radioisotope of plutonium is used in household smoke detectors, I put the pictures in the slide. Okay, and lastly, radioisotope. Others radioisotope are used in radiotherapy and gamma sterilization in medicine. Okay, if you guys want to know that 1 in 2 individuals in the Western world will benefit from nuclear medicine in their lifetime. Okay, as a conclusion, okay, we can conclude that the organometallic chemistry of uranium and thorium is reasonably well developed and show many similarities to that of the lanthanoids, except that thorium and uranium occur in numbers of oxidation state and are larger than the typical lanthanides ion. Okay, here is the list of reference from our group in this presentation. Okay, that's all from us. Thank you.